exercise 2, and this one states, prove theorem 2 mentioned earlier in this video, and we're given a hint, use either definition 2 or the squeeze theorem. Here is theorem 2, I just copied and pasted. Let's just scroll up to see where this was found. Where's theorem 2? How far away is it? So let's see where it was. I'll show you there. So we passed theorem 3, and there is theorem 2. So this is the one we had written over here. And basically, if the limit as n approaches infinity of the absolute value equals 0, then we have the limit without the absolute value is also equal to 0. So let's scroll all the way back down. Fascinating stuff. Just wanted to go there to see where in the video it was. So way far up in the video. It was a pretty extensive video. So let's keep going, and now there's exercise 2. So there's a theorem, just to double check. So recall of theorem 2 right here, so limit like that. Yeah, so now what we could do is, well, solution 1, let's use squeeze theorem, and then solution 2, we'll use definition 2. So what we could do is, so if the limit of the absolute value of an as n approaches infinity is equal to 0, then what we can even write is, so if limit as n approaches infinity, an absolute value is equal to 0, then what we could write is the limit as n approaches infinity of negative a absolute value of an. This equals to, we'll just use limit laws, take the negative out. This becomes, well, negative. Now limit n approaches infinity of an just equals to, well, this is 0. So negative 0 just equals to 0. So yeah, that just equals to 0. And now, since we have negative an, negative absolute value of an is going to be, well, less than or equal to an, where this is less than or equal to the absolute value, because remember, that's always, just make it always positive. This one's always negative, so that's always going to be less than or equal to an. So now it gets squeezed inside. So thus we have, limit as n approaches infinity of an, well, this is, remember, both of these are going to 0. This is going to 0. This is going to 0. This one gets squeezed, has to go to 0. So thus limit as n approaches infinity of an equals to 0 by the squeeze theorem. So yes, the squeeze theorem is quite amazing. It's very straightforward and quick. So there it is. Yeah, so now let's solve this very same theorem, but now use solution 2. I mean, look at solution 2, which is using definition 2, which is, again, a precise definition for sequences, as illustrated in exercise 1 as well. So we have here definition of sequence. An has this limit, and we write the limit as n approaches infinity of an equals L, or an approaches L as n approaches infinity. If for every epsilon, number epsilon greater than 0, there's a corresponding integer n, capital N, such as we have this case. If an integer, if any integer n greater than, if all integers n greater than capital N, then we have this scenario: the difference an minus L, the absolute value is less than this epsilon. Then this is the limit. So again, just recap it. I also need to recap because sometimes this takes a while for the precise definition. The terminology that mathematics book or the calculus book uses is. Yeah, it appears non-intuitive, but once you dig your head into it, it's pretty straightforward. So if we use this definition, but in our case, so L equals to 0 in our case, because we have, the theorem is the absolute value is equal to an equals 0. So we're looking at that. So the limit is 0, and also we're dealing with absolute value. So what we have is, so in our case, we have this and, let's write and, so we have limit as n approaches infinity of absolute value of an, like this, equals to, well, 0, and this is if n is greater than capital N, then n minus 0, like that, epsilon. Or in fact, to be more complete, we'll write this as an absolute value here, so we'll have absolute value of an minus L, like this, less than epsilon, but this becomes, well, this becomes absolute value of an minus 0. So the 0 just goes away, which equals to, this one becomes, well, absolute value of an, just to illustrate the point, which is the same thing as writing absolute value of an less than epsilon. So in other words, this is the same thing as removing the absolute value sign. Same thing. Yeah, so thus this fits also for fits. So this definition fits also for removing the absolute value sign. So limit as n approaches infinity of, well, an, and this just equals to 0. So yeah, if we have this is exactly the same thing. We're gonna have we're gonna have the exact same scenario where n is greater than n, then we have this scenario of but instead of that we just remove that an. So we have this exact same thing. Yeah, so thus we have limit as n approaches infinity of absolute value of an if this equals 0. This also equals to the limit as n approaches infinity of an, like that. So yes, there's the theorem. And here's for completeness, let's write the definition inside this little bubble here as well. If n greater than n, then we have an minus L less than epsilon becomes, well, an minus 0 equals to an, like that. Same thing, less than epsilon. So yes, fascinating stuff indeed. So thus limits are one and the same.